welcome back. In previous class, what we have seen that how to construct linear oscillator as well as non-linear oscillator, and what we found that linear oscillator, meaning of linear oscillator, we have taken very simple LC circuit, and after that we have constructed the linear oscillator, that is also called harmonic oscillator. And in case of linear oscillator, and we have already know that if I have second order system where A belongs to 2 cross 2 matrix and X is also obviously belongs to R2, and if eigenvalue of A matrix is purely imaginary, then what happens that each and every closed curve in this two-dimensional plane is somehow become some kind of orbit. Okay, so I have taken the case of linear system. So somehow I have connected. You can see that everywhere where this orbit, if you just change initial condition, then I have some other orbit. So this kind of oscillator is called harmonic oscillator, and this is structurally unstable. Okay, and you can see that second problem is that is function of initial condition. So if initial condition is here, then radius of this orbit is like this. Okay, so based on initial condition, radius is going to change. What we found that using some kind of non-linear circuit, and in previous class we have seen tunnel diode, it is possible to construct some kind of, again, periodic kind of orbit which has little bit different behavior, and behavior is like this. So I have suppose this is my orbit. So, and if I start in the nearby of the equilibrium point, this is trivial equilibrium point, and after that what happens that locally trajectory is diverging, but if you see the global phenomena, suppose if you take initial condition like this, then trajectory is going to converge here like this, something like this. So what happens if you see the phenomena, and this is x1 x2, and now case is x dot equal to fx. So I have nonlinear system. Again, I am just considering nonlinear system in plane. It means that two-dimensional nonlinear system. And what we found that as t tending towards infinity, so behavior is same like equilibrium point, means all trajectory except this trivial one are going to converge to this particular orbit, and this orbit has similar kind of behavior like equilibrium point. Why I am telling similar kind of behavior? So what is behavior of equilibrium point? If you start from the equilibrium point, you are going to stay there. Similar kind of things here. If you start in this orbit, then you will rotate, but you are not going to leave this orbit. That is the property. And this isolated orbit is called limit cycle. So this is not called limit cycle because here I have continuum of the orbit, but here I have isolated orbit. This is called limit cycle. Okay, and it is possible to show that limit cycle kind of behavior is only possible if we are going to consider some kind of nonlinear system. Okay, due to that reason, whatever oscillator we are seeing inside the lab or anywhere in medical field, all are constructed based on the analyze or design based on the nonlinear control theory. Okay, one more important point, what we found that if I have isolated means periodic orbit, then I can construct oscillator, and oscillator has several different applications in field of chemical engineering, in biological engineering, lot of places. Okay, so now could you please tell me the disadvantage of limit cycle, or what do you think? It is always advantageous. Anyone? So could you please comment about the disadvantage? If anything in your mind, then please comment. Baby Dina, what do you think? That limit cycle is always advantageous or there exists some disadvantage? Iram Taslima? Okay, I will tell you some situation. Actually, what happens that limit cycle has some disadvantage also. What is disadvantage? You try to see that suppose I have designed some kind of mission or simple case. Suppose this is CTA and this is CTB, and aeroplane is flying from here, and we are hoping that that is going to land here. But what happens in between? Some some phenomena occur that due to some kind of bad weather condition or some and due to some kind of mistake, what happens, all engine going to become fail. Okay, it means that somehow my system become autonomous, I cannot apply any external force. And suppose that if this kind of orbit comes into picture, then what happens, is it possible to control the plane, or is it possible to again safely land the plane? It is impossible, because they create some kind of invariant orbit, and finally after some time when fuel become int, then they what happens, that finally it burned. Okay, similar kind of things happen. Suppose that I have to launch some kind of geostationary satellite, and if I do not analyze each and every component of control system or mission, then what happens that if somehow this kind of limit cycle will involve, then I cannot able to place my satellite on some specific orbit. Due to that reason, whenever you are designing mission, whenever suppose that some kind of air wave, some kind of water wave, some kind of things comes into picture, and if this kind of phenomena comes into picture, then things become very dangerous. Okay, and due to that reason, if you are working on some mission, then also you have to understand that, or you have to analyze that there do not exist any limit cycle, so that kind of things is required. But suppose that if you want to launch some kind of geostationary satellite, and somehow you are able to make sure that I have some kind of limit cycle of behavior, that is quite fine, because in presence of some disturbance also, again I will get some kind of isolated orbit, so I have advantages also. Okay, and due to that reason, this area of research is very active, still active. Why that is very active? It is possible to show that for planar system, two-dimensional system, one can able to give some kind of criteria such that one can able to give guarantee that there exists some kind of limit cycle, or there do not exist some kind of limit cycle. But for higher dimensional case, it is not obvious. Okay, so I have seen some kind of literature for third order. Still for fourth order, fifth order, or nth order, it is very difficult to generalize. Okay, so and why people are teaching this kind of subject, you have just seen that there are several applications. Apart from that, we are hoping that after PhD, a student will take this kind of challenging problem and they try to develop some kind of theory such that for three-dimensional case, fourth-dimensional case, what is condition for existence of limit cycle. Okay, so whenever we are designing some kind of power converter or some kind of power system kind of circuit, there also we are trying to avoid this kind of things. Okay, so whenever you are constructing some kind of circuit, then please see the possibility of limit cycle. Okay, during tutorial I will send some kind of examples also, but obviously for second order system. So in this lecture also I am going to limit myself for second order system, because for second order system, that is some kind of planar system, so using some kind of closed orbit, we are able to exclude some region or we are able to include some region, and due to that region it is possible to give some kind of criteria to detect the periodic orbit. Okay, and out of that three criteria One is called Poincaré-Bendixson theorem. Second one is Bendixson criteria, and third one is index method. So these three things I am going to discuss in today's lecture. So sometime I am going to involve theory to search that there exists limit cycle or periodic orbit. More generally, why we are telling periodic orbit? Because limit cycle is very special case, but periodic orbit is general case. It might possible I have orbit, but all orbit are connected. So we are just going to see the existence of the orbit, and after that obviously we will see the uniqueness of orbit, that whatever orbit that is going to exist in two-dimensional plane, that is unique or not. Okay, so let us first I am going to discuss one of the very celebrated theorem in this particular direction. Okay, and since due to some limitations I am not going to discuss the proof, so I am just going to give the intuition, and due to that reason here I have just retained the obvious consequence of that theorem, that is a small part of that theorem is called lemma. Okay, so I am going to state this lemma without any proof, and proof is obvious, you are able to understand the proof. So first try to understand that what basically this lemma Poincaré-Bendixson criteria is telling. They are telling that consider a system, obviously again you can see that this is two-dimensional system, and let M be a closed bounded subset of the plane. Okay, so what theorem is suggesting, or what this lemma is suggesting, that in two-dimensional plane I have some closed bonded subset. Why I am taking that? Because we know that in two-dimensional plane, if I have some kind of equilibrium point, then if I start from this equilibrium point, then I am going to stay there. But if I start nearby of this equilibrium point, then I have two different kind of behavior. What is two different kind of behavior? Either I can all trajectory, that is starting nearby of equilibrium point, that is going to converge towards this equilibrium point in some way. It might possible I have just drawn this kind of vector field, but it might possible I have different vector field also. But second thing is that if you start nearby of this, it might possible that you can diverge. So two things I have. Okay, now you try to see that in this plane, if something is diverging, it means that locally that become unstable. This equilibrium point is locally unstable, we are telling, because when I have already told you that whenever we are searching the behavior of nonlinear system, we are using the word local only, because I have several equilibrium point, isolated equilibrium point in case of nonlinear system. So I cannot talk about stability of whole system. I am just able to talk stability about some equilibrium point. So this equilibrium point has some kind of diverging behavior. Now suppose in this plane, if I have some kind of closed and bounded subset of the art or the two-dimensional plane, what I mean to say, that M, that is subset of R2. So M belongs to R2, but that is not whole plane, that is subset of this plane, but that is closed and bounded. Okay, then what we are telling, that next thing, that M contain no equilibrium point or contain only one equilibrium point, such that if you going to calculate the Jacobian dou f by dou x, at that point has eigenvalue with positive real part. Okay, so could you please tell me, Silpi, could you please tell me that if eigenvalue is positive, okay, for nonlinear system about some equilibrium point, then what is behavior of that equilibrium point? Silpi, have you understood my question? What I am telling, suppose you have some kind of nonlinear system, okay, and this about this, if you calculate dou f by dou x about this equilibrium point, then what happens, whatever eigenvalue of this matrix A on the neighborhood of this, that has positive real part. Okay, so I have positive and alpha is eigenvalue that is greater than 0. Then what is behavior of the equilibrium point? Silpi, are you here? Okay. Baby Dana?
Yes, sir.
So if eigenvalue is positive, means real part of eigenvalue. So
Unstable.
so unstable, and what is unstable focus or unstable node
Unstable focus, sir.
focus? So since I am talking about the real part, is it possible to claim that might be unstable node also?
Yes, sir.
Yes. Why? Because any real number can be written in form of complex number also. Due to that reason, that is either unstable locus or unstable node. Okay. Anyone has confusion on this? So you can see here that whenever we are talking about M, so it might possible there is no equilibrium point, but still I have some kind of orbit. We will see that case. And after that, what we are telling, that second thing, that every trajectory starting in M stay in M for all future time. Then we are telling that M contain a periodic orbit x dot equal to fx. So what basically we are telling, so I am going to again show this kind of each and every part of this lemma using this. So what I am telling, that suppose this is whatever orbit I have considered here, this closure I have some kind of closed and bounded orbit, and after that we are giving guarantee that if something is a start nearby of this, then that is going not going to leave here. It means that they are going to converge here. This kind of claim we are doing. Suppose that even if this equilibrium point is not there, I have this kind of region. So suppose if I exclude this kind of equilibrium point, still suppose that if I am in this region only, that is annular region, so I have a region with some kind of hole, you can see that no trajectory is going to stay here, finally they are going to converge here. Okay, and if that kind of things happens, then we are telling that this particular orbit is periodic orbit. Okay, so this theorem is basically come from the intuition, or very clear from the intuition. So similar kind of things we are stating in this particular theorem. Now let us try to see our lemma. Lemma means a small part of the theorem. Now we have to see that we have to develop some kind of mathematical condition such that we are able to see that whatever trajectory that going to start in the, if I have equilibrium point, so nearby of equilibrium point, or if I don't have equilibrium point, then inside the equilibrium point, that is going to trap inside a set or not. Okay, so due to that reason I have to develop something, or I have to understand something from the, and I have to relate whatever things I have stated in theorem with some kind of mathematical formulation. So let us see that what I am going to do. I am going to first construct some kind of closed curve. And how to construct closed curve? So you can see that if I have two-dimensional plane, so in this two-dimensional plane, it might possible I can construct some kind of curve like x1 square plus x2 square equal to c, or I can also take very general case x2 square equal to c, or something some alpha x1 square plus 2 gamma x1 x2 plus beta x2 square equal to c, something like that. Okay, just I have to make sure that whatever curve I am going to construct in this two-dimensional plane, that is closed, and after that that is bounded. Okay, another thing, I am going to assume that whatever curve that is continuously differentiable. Why that is continuously differentiable? You can see that inside this curve, this function is involved. Okay, so whenever we are going to see the rate of change or vector field across this curve, so I have to involve the dynamics, and that is possible only if I have to I will calculate the gradient of this curve. Okay, so if you calculate the gradient of curve, then vector field is involved. And somehow I have already told you in the when I have started the phase plane analysis, x dot equal to fx. So here fx is also interpreted as a vector field at some point x. So each and every point in a space I have certain kind of vector field. Okay, so I have to identify the vector field, and based on that vector field I am going to give guarantee that trajectory is going to trap or not going to trap. Okay, so let us try to see the how basically we are claiming this kind of things, that trajectory is going to trap or trajectory is not going to trap, that kind of things. So for that, what I am going to do, I am going to see the vector field fx at a point x on the curve. So first I have constructed some curve. Suppose I have to see the periodic orbit or closed orbit in this region. Then what I am going to do, I am going to construct the curve, and after that what I am going to do, that I am going to see the inner product of gradient of this function delta v. Okay, we know that how to calculate gradient. I hope that, suppose if v is function of x1 and x2, then gradient of this is dou v by dou x calculated at x. Okay, plus dou v by, so we are writing like this, dou v by dou x calculated as x, and after that second one is dou v by dou x2 calculated at x. Okay, and after that what we are going to do, we are going to calculate the inner product with this f1 and f2. So I have some kind of vector. So you can see that this matrix is 1 cross 2 matrix. So 1 cross 2 matrix. So I have to multiply something like f1 and f2. Okay, or vice versa, f1 and f2 you can take here. So whatever representation I have used, same kind of representation now I am going to write here. So what I am telling, that I'm going to multiply with this kind of things, f1, and after that f1 and f2, and this quantity is transpose of that. Okay, then I have 1 cross 2 and here 2 cross 1. So finally I will get 1 cross 1. Okay, so what I am going to do, that I am going to check that this fx and gradient of this and their inner product, that should be less than 0. If that is less than 0, then what I can give guarantee, that whatever vector field, that is in inward direction. Okay, similarly if this become positive, then you can see that vector field point outward, and if this equal to 0, then vector field become tangential. Okay, so what basically we are telling, suppose you have closed curve and I have some kind of dynamical system like x dot equal to fx, and I know the equation of this curve, that is vx equal to c. So if vector field has this kind of direction, then it is possible to show that fx and after that inner product with this gradient of this, that is in inward direction. If that is less than 0, if that is greater than 0, then the outward direction, and if that equal to 0, then that is tangential to this, like this. Okay, so now by seeing these calculation, you are able to understand that when basically closed orbit comes into picture. So trajectory can leave a set only if the vector field points on outward at some point on the boundary. Okay, so in order to confirm that in this particular boundary I have some kind of periodic orbit, so if direction, if the dot inner product of fx with the gradient, and if that comes like this, or if that is greater than 0, then I can tell that actually trajectory is not going to confine on this particular orbit, they are going to leave this orbit. Okay, so now let us come to this note, that for a set of the form. Suppose that I have constructed some kind of closed orbit and I have defined closed orbit Vx is less than c for some c greater than 0. Trajectory are trapped inside m. So I have defined m like this. So m is some kind of closed region, and after that c is some radius of that. So either I am here or inside this. So that is the meaning. So this is m is the region. If that inside m, if this kind of condition is satisfied, and on the boundary, if we are just there, you no need to look everywhere, just you can see the boundary, and across the boundary if this condition is satisfied, then what we are going to see is, to tell that whatever trajectory that is going to trap inside this m. Okay, anyone has confusion on this? So what we are going to do, in order to give trapping, that all trajectory trap inside this, just I have to check on this particular curve. There is no need to check everywhere. Just you can check across this curve by checking these two, and we know that how to define dou. This is nothing but dou v x by dou x1 multiplied by f1x and plus dou vx dou x2 f2x, and after that you have to just check that is less than equal to 0. So if that equal to 0, then trajectory is tangential to this curve. So again that is not going to leave. If that is less than 0, then that is always pointed inward direction. Okay, again that is not going to leave. Okay, now based on this I can also able to understand something more, that because what Poincaré-Bendixson theorem is telling, they are telling about two cases. One case that they are telling that I have some kind of region where there is no equilibrium point. Okay, one case it might possible I have an stable equilibrium point about that, and I can check by calculating the Jacobian. But it might possible, suppose that whatever region I have selected that contain no equilibrium point. So for simple same kind of example you can take. Suppose I have here unstable equilibrium point. Now I am just going to concentrate on this region only. I am going to exclude this region. I am not worrying about this region. So you can see that in this particular region, particularly in this region, I don't have any equilibrium point. Now we are going to check that inside this region I have some kind of periodic orbit or no. So this region can be defined like, initially if you just write like this, it means that 0 is also included. But if you write Vx less than equal to 0 and Wx greater than equal to C, it means that I am going, this particular region is defined as a Wx greater than equal to C1, where C1 and C2 both positive I am taking. So I am just going to concentrate about this region. So I will show you this region with different color, then you are able to understand. So basically in this region there is no equilibrium point. If you include this region, then obviously I have equilibrium point. So if that is unstable, then that is okay. But even if I don't have equilibrium point, and if inside M I have to check on again on this curve Vx equal to Ct, if this kind of condition is satisfied. But inside, if this kind of condition is satisfied, means across, if you check two extreme curve, one curve here and one curve here, if trajectory will satisfy this kind of condition, fx and after that gradient of omega x greater than 0, then I can tell that whatever vector field, their direction is outward from here, and whatever vector field here, their direction is inward from here, like this. At boundary I am telling, not inside. So if this kind of condition is satisfied, then we are telling that there exists periodic orbit in this annular region. Okay, anyone has confusion on this? Then please let me know. So from figure also you can see here that what I am telling, that suppose this is closed region, and after that I have inside this, suppose this region is excluded. So in order to make sure that there exists some kind of periodic orbit, the direction of vector field on this particular surface that should be looks like this. And how to confirm that it looks like this? You have to do the inner product of that function or vector field with respect to that particular curve, so gradient of that curve, and you have to make sure that here, since I am talking about outward direction, so that is greater than equal to 0. And in order to show this, I have to just make sure that this is, and omega, that should be here v should be less than equal to 0. So in this way, I can tell that whatever orbit, this kind of orbit, that is periodic orbit. So I do not know what kind of shape is basically coming. We are just going to confirm that there exists some kind of periodic orbit or not. Now let us check the statement of lemma using the help of some example, and this example we have already seen. So someone, could you please tell me that if I have this kind of system, and here you can check the eigenvalue, so -1 and 0. So Vinay, could you please tell me that in this case, this particular system has which kind of behavior, that is node or Focky or some kind of saddle or some kind of orbit? What kind of behavior we have in this particular case? You can see 0, 0, -1 and 1 I have. So what is eigenvalue?
Principal is 0, 0, I think, sir.
So 0, 1, -1, 0. So you can see that in order to calculate eigenvalue, I will calculate lambda I minus a and determinant of this. So lambda, square plus 1 equal to 0. So lambda is plus minus I.
It's a plus minus j. Yeah.
Plus minus j. So if lambda equal to plus minus j, so it means that I have here I or j, whatever you want, you can write.
Yeah.
So this is complex. Then what is behavior? So I have purely complex eigenvalue. Then what is behavior? That is periodic orbit. Okay.
Periodic.
In case of saddle, one eigenvalue, both eigenvalues should be real. One should be positive, another should be negative. Then we are telling that as a saddle. Okay. Look, Focky or whenever we are talking about some kind of complex eigenvalue, at that time we are telling that a stable focus or unstable focus, that is based on the real part of alpha, because beta either you can take negative and positive, that not going to change the behavior. Okay, so slowly please do practice, then you are able to understand. Now you can see that if I consider any annular region, why I am considering annular region? Region is that you know the behavior at the equilibrium point. If you start from equilibrium point, you are going to stay there, and due to that region, in order to see the possibility of periodic orbit, people are excluding this point. So how to exclude this point? You have to make some kind of closed surface across that equilibrium point, and after that you can take another surface. So, and I am assuming that I have some function Vx, and lower bound of that is C1 and upper bound is C2, like that. And so this region I have constructed, and after that I have constructed this kind of surface x1 square plus x2 square, okay, equal to Vx. So I have constructed some kind of circular region. Okay, after constructing the circular region, now I have to show that there exists some kind of periodic orbit or not. So what happens that I have to calculate the dot product of f1 fx. So here you can see that this is nothing but f1 x1 x2, and this is f2 x1 x2. After that I have to calculate the gradient. So dou v by dou x1 is 2x1, dou v by dou x2 is 2x2, and after that just I have to take the dot product of that, and if you calculate that dot product, it is possible to show that is 0. Okay, why I am telling 0? You can see that in place of I have to do f1, and after that, or you can dou v by dou x1 into f1, after that dou v by dou x2 into f2, and if you check this calculation, then that is equal to 0. Okay, that is straightforward. Okay, so it means that at the boundary point, everywhere, whatever vector field that is tangential, okay, M is already closed, bounded and free from the equilibrium point, because whatever region I have constructed, you can see that this region, this annular region, there is no equilibrium point, so that is free from equilibrium point. After that, what we found, that on the boundary point, in each boundary point, this boundary point also and this boundary point, if you calculate the inner product of vector field and the gradient of this curve, then that equal to 0. It means that everywhere I have this kind of vector field, and if I have this kind of vector field, you can see that if you start here, you are going to stay there. Similar kind of situation here. So if you construct any other orbit, similar kind of construction I have, because any orbit you can consider, any closed circle you can consider, for that, on the boundary point of that, I have this kind of result. It means that trajectory is going to trap. Okay, either they are going to trap on the boundary or inside the boundary, both are same. So from Poincaré-Bendixson criteria, I can tell that I have periodic orbit, and I am also telling I have no isolated periodic orbit. Why? Because what we found, that any orbit you can consider, any closed surface you can consider or construct for this system, then what happens, that if that is circular, then their inner product of that vector field with gradient function that equal to 0. So every point, okay, so about every point one periodic orbit is passing, and same kind of things we have also analyzed whenever we are doing the phase plane analysis. Now let us try to take another case. So first case is for linear system. Now I am going to generalize it for nonlinear system. So I have constructed some artificial example like this nonlinear system. Here you can see that I have equilibrium point, and how to calculate equilibrium point, just you can put x1 dot equal to 0 and x2 dot equal to 0. So equilibrium point is 0 0, and this equilibrium point is unique. It is possible to show that apart from this, there is no other possibility. Only one equilibrium point I have 0 0. Okay, so again, what Poincaré-Bendixson theorem is telling, either I have unique equilibrium point, one equilibrium point inside the closed region, or no equilibrium point. So just we have seen there is no equilibrium point. Here we are telling only one equilibrium point. And if I have unique equilibrium point, then I have to check that real part of that eigenvalue should be positive. Then only I can talk about the existence of periodic orbit, and due to that reason, I have to linearize the system about that particular point. You all are already well aware how to linearize dou f1 by dou x1, dou f by dou f1 by dou x2, dou f2 by dou x2, dou f2 by dou x2. So like that we are doing. So same kind of calculation, please do calculation by yourself. And after that, since I am linearizing about x equal to 0, so put x equal to 0. After that, what happens, you can see that I come up with this constant matrix. It means that my system, about nonlinear system, my original nonlinear system, whatever I have taken, about this equilibrium point that represented as some equivalent linear system. Now if you check the eigenvalue of this system, you can see that that is complex, and real part of this complex eigenvalue is positive. And just now we have discussed that if real part of the complex eigenvalue is positive, then I have some kind of unstable kind of behavior, unstable foci or unstable focus I have. Okay, so I have unstable focus. It means that trajectory is not going to stay at 0 if we are going to start nearby of 0. That is the meaning. Okay, now what I am going to do, I am going to do construction of some closed curve, and again same curve I am going to construct. So I am assuming that there exists some kind of circular region. So I have constructed circular region by x1 square plus x2 square, and here C greater than 0. So now by construction of this region, it is possible to show that M is closed, M is bounded, and contain only one equilibrium point, that is unstable, because if you see the construction of this in two-dimensional plane, this is my unstable equilibrium point, and after that I have constructed circle. So this circle is closed, bounded. So whatever region I am talking about, this whole region, that is closed, bounded, and only contain one equilibrium point, and that equilibrium point is unstable. So due to that reason, that is also the statement of Poincaré-Bendixson theorem. So that is quite okay for analyzing the periodic orbit. And after that, now I am going to check on this surface that fx dot product with or inner product with delta v, means gradient, that equal to less than equal to 0 or not. Okay, so if that is less than equal to 0, then I can give guarantee that trajectory is going to trap. Okay, so same kind of things I have done. I have just done calculation. Please do calculation by yourself, because that is pretty obvious. Dou v by dou x. So I have x1 square plus x2 square, and after that just I have calculated the partial derivative with respect to x1. So that is 2x1. Similarly, with respect to x2, so 2x2. Due to that reason, this term dou v by dou x, that is 2x1, dou v by dou x2, that is 2x2. And after that, f1 means since I have second order system, so I have vector field in x1 direction, vector x1 dot direction, and vector field in x2 dot direction. Same kind of things I have substituted here, and after that I have done the manipulation, and you can see that if you have this kind of term 2x1 x2, it is possible to show that 2x1 x2 is less than equal to x1 square plus x2 square. So you see here, I cannot use maintain same kind of sign if I want this kind of inequality. So what we are going to do, first we are going to take the worst case. Most of time whenever we are formulating inequality, at that time we are considering the worst case. Worst case is that since x1 and x2, I don't know the value of x1 and x2, sometimes that is positive, sometimes that is negative. Okay, so I am going to consider the positive value. Okay, and positive value in worst case, that is equal to this, and due to that reason this inequality comes into picture, and after that I have this. Now I know that x1 square plus x2 square is c, so I have c here and I have 2c here, so 3c comes into picture, and after that x1 square plus x2 square is c square, so 2c square. Now in order to make sure that there exists some kind of periodic orbit, okay, what we have to do, we have to make sure that this is less than equal to 0. Okay, so how to make sure that it is less than equal to 0? If c is greater than equal to 1.5, so it means that I can only able to give guarantee that if whatever region I have constructed, so you can see that region I have constructed like x1 square plus x2 square, and after that I am telling that Vx is less than equal to C. So if that is less than, and what I am telling that C should be greater than equal to 1.5. So if C is 2, 4, 5, something like that, then only there exists a periodic orbit. Suppose that if someone is taking C that is not greater than equal to 1.5, they are going to take C as a 1, then Vx equal to 1, that is closed orbit, but that is not going to allow some kind of periodic orbit. Okay, so in this way we are able to understand that when periodic orbit comes into picture, when periodic orbit not comes into picture. And from whatever example I have taken, suppose that here I have Earth, and suppose by some calculation in higher dimensional, again since I am talking about geostationary orbit, so at that time you have to consider 3 dimensions, and suppose that I have developed some kind of criteria, so it is possible to show that under what condition some kind of isolated orbit comes into picture, some kind of limit cycle comes into picture, under which condition some kind of limit cycle node comes into picture, what distance if I maintain such that I have geostationary kind of behaviors, I have periodic kind of behavior. Okay, now let us come to the, so this is a story about the first criteria, that is very celebrated, Poincaré-Bendixson. criteria. Now I am going to discuss the second criteria, that is called Bendixson criteria. And basically this criteria most of time we are using to rule out that existence of periodic orbit, because I have already told you that sometimes it is better to avoid periodic orbit, otherwise some kind of trapping happens. And what what happens that if trapping kind of things comes into picture, I cannot control that phenomena. Okay, so due to that reason I have to avoid the periodic orbit. You can avoid periodic orbit by applying some kind of control action, or generating some kind of energy. Internal external energy is always required in order to violate that kind of orbit sometime, and that energy should be much more enough. Otherwise what happens, you know that if I go outside of that orbit, and orbit is the some kind of limit cycle is some kind of invariant state. So what happens if that is invariant state, then what happens, trajectory again try to converge to that limit cycle. And due to that reason we have to make sure that how to avoid that kind of periodic orbit or limit cycle. Okay, now let us come to the second condition, that is called Bendixson criteria. And basically this criteria is very simple, and this criteria most of time we are just using to make sure that there do not exist periodic orbit. Okay, so somehow I want to remove the risk of the limit cycle or periodic orbit. So if on a simply connected region, you can see that I have used simply connected region. What does it mean? Suppose that we are telling that I have some region and that is simply connected. It means that if you consider some another region, so I have this region D and this is C, that is subset of D, then what happens that we are telling that if this region is closed, then whatever region you are going to make here, that is subset of that. Okay, that is not always true. Suppose I have some kind of hole here, or some kind of anal region is here. You can see that this region is inside this D, but that is not this subset, so that is not connected. Okay, so in order to avoid, we cannot going to consider this kind of situation. Poincaré-Bendixson criteria is going to consider this kind of situation, but here whenever we are applying Bendixson criteria to avoid or ignore the periodic orbit or possibility of periodic orbit, there we are assuming that whatever region I am going to consider, that there do not exist any kind of hole. Okay, so intuitively we are avoiding the hole. We are telling that everything means whatever closed things I am going to make, all are somehow, all do not have hole. That is the meaning of simply connected region. Okay, now if this dou f by dou x plus dou f2 by dou x2 is not identically 0 and doesn't change the sign, then I can give guarantee that this system x dot equal to fx has no periodic orbit lying entirely on D. So that kind of things I can able to generalize. So what I have to do here, there is no need to check the inner product of function and with gradient. Okay, here just you have to check the combination of this, and we have to just make sure that is not identically equal to 0. Okay, that might have greater than 0 or less than 0. Okay, so if that is not identically 0, then I can give guarantee that there do not exist the periodic orbit. And proof is very simple. You can see the proof. Proof is like this. So if I have this kind of system x dot equal to fx, so you can see here I can also able to write dx by dt equal to f1x. I have two component. After that dx2 by dt equal to f2x. Now if you take the ratio of these two, dx2 by dx1, that is nothing but f2 by f1. Okay, if I have some kind of orbit, then this relation will always satisfy. Okay, so suppose if I have orbit, it is possible to show that ratio of this f2 and f1, that is ratio of dx2 by dx1. Okay, now what I am going to do, I am going to take any closed orbit gamma. So in closed orbit gamma, so what happens that in that particular closed orbit you can just multiply here, and after that what you can do, you can take the integral then I have, this is also called line integral about that closed curve gamma. So I have closed curve here, and after that I am going to calculate the line integral, and if I have orbit that equal to 0, from here that is obvious. Okay, now what I am going to do, I am going to change this line integral, because I have to make sure that inside this also there do not exist any kind of closed orbit or periodic orbit. So for that I am going to change this line integral into some kind of double integral. Okay, so if you see the vector calculus, one theorem you might have learned during your first year of engineering course, that is called Green's theorem. And what is main idea of Green's theorem? That is going to relate the line integral around a simple closed curve. So I have some kind of curve C to a double integral over the plane. So I have something in plane. So using double integral on plane, and suppose in the double integral I have some region D. So they are telling that how to relate this. So somehow it is converting line integral to something like double integral, and after converting line integral and double integral, you can see here whatever negative sign is here, that is somehow converted into positive sign. So this is just from the application of Green's theorem. So please check the Green's theorem. So idea is that line integral to surface integral or double integral I am going to do. And if you are in two-dimensional space, then that is also called a Stokes theorem. Okay, so I am not going to going on that detail. So I have this kind of things, and you know that this integral equal to 0 only if this quantity equal to 0. Okay, so if this quantity equal to 0, then I have periodic orbit. Okay, if this is greater than 0 or less than 0, then I can give guarantee that we cannot find a region S such that the last inequality hold, hence there is no closed orbit entirely in D. In that way, so just I have to check now that this should not be 0. If that is 0, then there may exist some kind of closed orbit. But if this condition is violated, if either that is positive and negative, then this particular condition is not violated. Okay, and this is condition for the closed orbit in two-dimensional plane. So we have derived from the line integral. Okay, so just now whenever you have some system, I have taken this system, again this is nonlinear system x2, and after that this. So what I have to do, I have to take partial derivative of f1 with respect to x1 and f2 with respect to x2, and after that what I have to do, I have to just make sure that whatever value that comes into picture, that should not equal to 0. So this is not equal to 0. Suppose that if b less than 0. So if b less than 0, so this quantity is already negative, and if this is also negative, then what happens, that this whole quantity is always negative. If you take b as a positive, then it might possible 0 is involved somewhere. I cannot exclude the possibility of 0. But if b is less than 0, then I can give guarantee that there is no periodic orbit. So in this way, we are able to avoid periodic orbit in two-dimensional case. Obviously, I cannot tell similar kind of result for 3 dimension. Okay, so for extra treatment is required in order to show that how to remove periodic orbit in 3-dimensional case. Now I have just talked two theorems, Poincaré-Bendixson theorem. So they are telling that first theorem is telling that how to find that there exists some kind of orbit by making some kind of closed surface, and after that taking the inner product of vector field with the gradient of that surface. Second methodology, whatever Bendixson criteria I have talked, that is telling that how to avoid the or how to remove the possibility of the existence of periodic orbit. Now in third criteria, that is called Poincaré index, so we are going to see relation between the existence of periodic orbit and equilibrium point. Okay, using that index, and again using this index we are going to see that what is the possibility, under what condition some periodic orbit comes into picture or not comes into picture. Again I am going to consider just two-dimensional case, x dot equal to fx, and after that we are we are going to see something, we are going to define something that is called index. Okay, Poincaré index. So how to define index? So in order to define index, what you have to do, so you have to consider the orientation of vector field at each point of some closed area C. So what I have done, I have taken this closed area, and suppose I have some kind of unstable node kind of situation. So if this equilibrium point is unstable node, you all are already well aware that trajectory is going to diverge from this equilibrium point if I have some kind of unstable node kind of situation. Okay, now what we are going to do, we are going to travel along this curve particular curve in counterclockwise direction. So I will take one vector field, and after that I start traveling in this particular direction, and after that what we are telling that the vector fx rotate continuously. So if from here you can see that if you are taking this kind of closed surface, then this vector, I am telling that here if I am traveling from here to here, then what kind of phenomena we are observing, that vector is going to rotate, and finally after 2 pi of rotation they are come to the same vector. Similarly I can tell that 2 pi k of rotation, again they will come to the same vector. So either you can take one rotation, two rotation, n number of rotation we are coming here. We are doing rotation in counterclockwise direction, means anti-clockwise direction, and returning to the same position and rotate by angle 2 pi k. So if you do one rotation, then you have 2 rotation, then you have 4 pi, like this. So for some k where angle is measured in counterclockwise direction, so whatever this value k is called the index of that closed curve C. Okay, so now using this example we are going to see how to calculate the index. Same example I am going to consider. So what happens, suppose that if you are started from here, then you can give some number. Okay, suppose that I am going to give this as a 1, this as a 2, this as a 3, 4, 5, 6, 7 and 8. Okay, now you can see that if you start from 1, so I am starting from 1, and after that I am going to 2, 1, and after that 2, so I am moving in counterclockwise direction. After that I go to 3, and similarly after one rotation I return to again the same one, like this. So I am telling that index of this is +1. So if I rotate in counterclockwise direction. Similarly, suppose that instead of this unstable, if I have some kind of a stable node, then I have this kind of situation. So vector field is pointing towards this, like this. Again you can give the number 1, 2, 3, 4, 5, 6, 7, 8, like this. Again what you can do the same here 1, and after that what I am going to do, either you can take this direction as a positive, that doesn't matter, so I can again plot same arrow, and after that if I move clockwise in counterclockwise direction, then only I can find 2, after that again 3, so direction doesn't matter, 4, 5, and again I have to do counterclockwise rotation. It means that index is 1, again 1. Okay, let us try to check that if I have saddle point, then what is condition. So you can see the result. The index of a node, a focus, and a center. Center means if both eigenvalue on the imaginary axis, again you can see that if you see the vector field is looks like this, tangential to this. Again if you give name 1, 2, 3, 4, 5, then you have to rotate in same direction, and due to that reason index is +1. So in this all case index equal to +1. Now try to see that index of a hyperbolic saddle is -1. So suppose if both eigenvalue is real and one is positive and another is negative, then what is the situation? And I hope that you all are are already understood that in that situation vector field, direction of vector field is converging in some direction but diverging in some other direction. Okay, so I have just considered the four extreme cases, and here you can see that again I am going to give name 1, 2, 3 and 4. Okay, now again you can start from here. You can see here that when I am here at this particular point, then I have 1. Now you can see that if you are moving here to here, then what happens, direction is just below, not the same direction. Okay, so below means somehow we are in order to pick up this I have to move in clockwise direction. So now your direction is 2 here. Now after that, suppose 1 and 3 are opposite, so 1 and 3, in order to pick up 3 you have to move 1 to 3 in the same direction. So again I have 3 here and 4 here. So it means that now I start moving in the opposite direction. Okay, and due to that reason, in case of saddle point I have index that is -1. Okay, so please do this drawing, and after that confirm this, because this proof is means this lemma is proof by drawing or seeing the vector field only. So similar way I have actually drawn the vector field, and after that index of closed orbit we have already seen that any closed orbit is +1, because whenever I have closed orbit, then what happens, vector field is tangential to the surface, so again that is +1. Index of a closed curve not in circle any equilibrium point is 0. So what basically we are telling, suppose I have some kind of closed curve. Okay, so closed curve, and what is meaning of difference between closed orbit and closed curve? Closed orbit means somehow I am talking about some kind of periodic orbit. But whenever we are talking about closed curve, so any curve can be closed. Just now in previous example we have seen that if b greater than equal to c greater than 1.5, then only I have periodic orbit. So beyond that I have orbit, and if c is in between, then I have closed curve but not orbit. Anyone has confusion in closed orbit and closed curve? Baby Dana?
Yes, sir.
Closed curve, do you have any confusion in closed curve and closed orbit?
No, no, sir.
Ankit, are you here?
Yes, sir. No
So
confusion, sir.
okay, so no confusion, then I will proceed further. So what happens if you have closed curve? So in closed curve, since there is no vector field, okay, so if or you can assume that if there is vector field, then what happens in closed curve, since all vector field is traveling in one direction only. Okay, so if something is traveling in one direction only, so I can not able to rotate. My vector field is not rotate and come to the one point, and due to that reason encirclement equal to 0. Okay, so please check this particular point. Now another point, that index of closed curve is equal to sum of index of equilibrium point. So what you can do now, whatever way I am checking by giving 1, 2, 3, 4, 5. Now you can take two equilibrium point inside that and draw two different curve. Suppose that you can take one point as a stable node and one point as a saddle, and draw the vector field, and after that draw one curve and do the calculation. It is possible to show that total index is nothing but that the closed curve is the sum of individual index. Okay, so please do calculation. Okay, using calculation one can do see this. So now in this way, using this lemma, we are just able to calculate the index. After calculating the index, now I am going to see the possibility, how to give guarantee that there might be possibility of periodic orbit or might not be possibility of the periodic orbit. So this corollary actually suggesting the same, and this is called the index method. So in index method, what they are telling that inside any periodic orbit gamma, there must be at least one equilibrium point. Okay, so you have already seen that whenever I am talking about periodic orbit, most of time inside this periodic orbit, there there exists at least one equilibrium point which has some kind of repelling property, okay, or unstable property. So same kind of things they are telling, that inside any periodic orbit gamma there must be at least one equilibrium point. Suppose the equilibrium point inside gamma are hyperbolic. So hyperbolic, whenever we are telling that hyperbolic means we are avoiding the possibility when both eigenvalue on the imaginary axis, okay, because if both eigenvalue on the imaginary axis, at that time I cannot comment about the behavior of nonlinear system, and due to that reason people are just concentrating on hyperbolic system where either both eigenvalue is real or complex. They are not considering those kind of case where eigenvalue is imaginary also, okay. Then n number of nodes and foci. So I have suppose n number of node and foci, and s is the number of saddle point. But we have seen just now that whenever I have node, whenever I have focus, whenever I have center, then what happens, that index is +1. But whenever I have some kind of saddle point, then index become -1, okay. So if s is the number of saddle, it must be n minus s equal to 1. So this they are telling that in order to existence of the periodic orbit, if periodic orbit exists, then this kind of condition is satisfied. This kind of condition is satisfied means inside the region, if there exists a node and if there s is the number of saddle point, and if that is equal to 1, so then, and if this relation will hold, then only I can tell that there exists a periodic orbit. If this condition is not satisfied, then I can tell that there is no a periodic orbit. So what we have to do now, just we have to see the region, you have to calculate n and s, and after that you have to see the difference. If that difference is not 1, then you are able to rule out the possibility of the periodic orbit. So most of time we are using index method to ruling out the possibility of the existence of periodic orbit, okay. So suppose now I have this kind of system, I have taken nonlinear system, because whenever we are talking about isolated orbit, that is not possible in case of linear system. So most of time now I am going to just talk about nonlinear system, and this is also course on the nonlinear system. And you can see that I have two isolated equilibrium point, and how to calculate equilibrium point, just you can put x1 dot equal to 0 and x2 dot equal to 0. So equilibrium point is 0 0. Now you have to see the behavior about equilibrium point, so you can just do the linearization about the equilibrium point. So if I have this kind of matrix, and if you see the eigenvalue of this matrix, it is possible to show that both eigenvalue is real and one is positive and one is negative, and due to that reason I have written saddle. So please check it, okay. Similarly, now I have written here a stable focus. It means that I have whatever eigenvalue of this particular matrix that is complex, and after that a stable focus means alpha less than, means the real part of that complex eigenvalue that is less than 0. That is the meaning. So the only combination of the equilibrium point that can encircle by a periodic orbit is single focus. Why I am telling this? Because we have just established this kind of behavior, that here if this kind of relation will satisfy, that n minus s equal to +1, so s is saddle, okay. So if saddle equal to 0 and n is the summation of all node, all focus, then that equal to 1. So you can see that 1 equal to 1. So if there is no saddle point, just I have some kind of focus that might be stable and unstable, then possibility of the periodic orbit comes into the picture. So same kind of things we are telling. Other possibility of periodic orbit in circle both equilibrium are ruled out. So if suppose that here you have created some kind of orbit, closed curve, and suppose this is node, and here this is node, and this is saddle point. So you can see here inside this node has the index +1 and saddle point has index -1. So what happens that since I have one node and one s, so just you can count the number and -s is there. So here 1 minus 1 that equal to 0. So here I am just talking about the number, we are not talking about the index. So if 1 and 1, so 0 is not equal to 1. Due to that reason we are telling that if I want to create some kind of region which will include both, then there is not a periodic orbit. Okay, but if suppose if you have constructed some kind of region like this, then there might be a periodic orbit. Okay, anyone has confusion on this? Now suppose if you are you draw one region like this, at that time I have to make sure that n minus 1 equal to 1. So suppose this equal to 0, then -1 equal to 1, that is not possible. Okay, so something that only encircle the saddle point, then I cannot tell that there exists a periodic orbit. Okay, if I have two different kind of situation is there, if I have this kind of situation. Okay, so using that method I can able to avoid that under which condition I don't have periodic orbit. Why I have this type of combination, then we don't have periodic orbit. Suppose that trapping is not possible because here one vector field of this saddle point that is going out, so I cannot going to remain inside this closed orbit. That is the interpretation. So now I am going to conclude the today's lecture. So what we found in today's lecture, that periodic orbit, so that periodic orbit is either harmonic or I have some kind of isolated periodic orbit that is called limit cycle. That has very several applications, several real applications, and due to that reason we have to understand that under which situation, and what we found that they have advantage as well as disadvantage also. So we have to know that under which case I have to make sure that there exists a periodic orbit, and somehow I have to remove those kind of case where periodic orbit do not comes into picture. Okay, so we have to talk about both possibility, and using the theory of this kind of theory, particularly for second order I have three different theory. Using that we can able to talk about the existence of periodic orbit. We don't know what kind of shape of the periodic orbit, but at least we can able to take about the existence of periodic orbit. So with this remark I am going to end the today's lecture. So thank you very much. If you have any question, then please let me know. Anyone?